All right, now let's look at the Newton form of the interpolating polynomial. Now in this case, we've got our points, x0, y0, x1, y1, x2, y2, up to some xn, yn. And if we have that, then the Newton form, and they call it Pn because it'll have degree n, Pn of x, well, we're going to need those n plus 1 coefficients, so we need an a0, that'll be the constant, then an a1, and you simply do a1 times x minus x0. So what we're going to do is for each coefficient, a sub I, we're going to do x minus, an x sub j, but we're going to do all of them such that the subscript here is smaller than the subscript there. So the next one, a2, will have x minus x0 and x minus x1. And we'll just keep that going until we get to our an, and we'll have x minus x0, we'll have an x minus x1, and that'll keep going all the way to x minus x sub n minus 1. And so that is the form of our polynomial. Now this is, it looks a bit nasty to evaluate, but actually will show that if you evaluate it smartly, so to speak, it's really not too bad. And so let's figure out then, well, how do we get our a0, a1, a2 up to an? Well, again, we can kind of exploit the structure here, because notice if I take Pn of x0, I'll get a0 plus a1 times x0 minus x0. Oh, but that's 0. Plus a2 times x0 minus x0 times x0 minus x1 plus, oh wait, but that's 0. And so that term's 0. And so we'll do the dot, 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 and up to the a sub n. But that also will have that x0 minus x0 term in it. And then x0 minus x1 up to x0 minus x sub n minus 1. But of course that's 0 as well. And so you see what we have is that Pn of x0 implies then that we get a0, but we also have our points up here, right? If we put in x0, we're supposed to get out y0. And so this tells us, I'm going to put it way over here, we get y0. Well, that's pretty easy to tell you then what a0 is. It's just y0. Then, similarly, if we do, I guess I didn't really, I'll put that back over here where we can see it better. And then we'll rewrite it in a bit here. So Pn of x1, though, now if we look at that, well, we'll get a0. And looking here, we put our x1 in there. And so we'll get plus a1 times x1 minus x0. But then for a2, we'll have that x1 minus x0 term. But we'll also have x1 minus x1. Oh, wait, but that's 0. Plus, dot, 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 plus, and we have our a sub n, we'll have our x1 minus x0, but we'll have an x1 minus x1, dot, 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 we'll have x1 minus xn minus 1. But again, all it takes is that one being 0, everything's 0. And so we see that if we take Pn of x1, that simplifies down to a0 plus a1 times x1 minus x0. But again, that's the point here. If we put in x1, we got to get out y1. So we get y1. So similarly then, if I did Pn of x2, well, I'm going to get that a0 term. I'm going to get the a1 term now, but the a1, remember, this value is what we're putting in. So we would have x2 minus x0. And similarly then, well, a2, well, that's going to get an x2 minus x1 because we had, well, actually, I guess I did it in that order, x0, and then x2 minus x1. So we did all the x's that had subscripts smaller than 2. But you see, so this works out this way, but everything else was 0, and this is equal to y2. And if you keep going that way and you get to Pn of xn, well, you're going to have your a0, you're going to have your a1, and you're going to toss in xn minus x0. You're going to have the a2 term. You're going to have xn minus x0 and xn minus x1 plus dot, dot, dot. Oops, ran out of room here. Okay. Plus, that final term, a sub n, we'll have xn minus x0, xn minus x1, all the way out to xn minus xn minus 1. And that's equal to y sub n. So now, if you write these in a little bit simpler form, what we end up with are n plus 1 equations and n unknowns, but they're really nice equations. They're a lower triangular system, and so we'll get a0, and now I'm going to put the y0 way over here. We'll get a0 plus a1 times x1 minus x0. That equals y1. And then we'll get a0 plus a1 x2 minus x0 plus a2 x2 minus x0 x2 minus x1 equals y2. And dot, 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 we'll keep going this way, and we'll get this last one, a0 plus a1 xn minus x0 plus a2 xn minus x0 xn minus x1 plus dot, 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 plus our an times xn minus x0 dot, 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 all the way up to xn minus x. Oh, I'm at the end of the page, so sorry, dot, 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 times, so let me just put this down here, plus an xn minus x0 dot, 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 times xn minus xn minus 1, and that all equals y sub n. So you see what happens is, I can tell you this right off, a0 is y0, so, right? a0 is y0. But then, once I know that, I can tell you that a1 is equal to the y1 there, minus the a0, but that'd be y0, and then divided by x1 minus x0. And then I could get a2. Well, we'll probably need to put it down here. A2 is equal to, now this one I'm probably best off actually, well, I've got my y2. Okay, so I've got that. And then minus a0, so minus y0. Okay, then minus that term, so minus a1, but that was right above me here, y1 minus y0 over x1 minus x0, and then times x2 minus x0, like that. Okay, so that's our A2. Now it's looking very complicated, but we don't have any numbers in there, and we would just continue this down and eventually be able to get AN equals something. Okay, so that's what's nice about this lower triangular system, is it is more efficient to evaluate than our original Vandermonde system, or the standard form that we looked at first. So it is more efficient to evaluate it that way. And then actually determine the coefficients that way. So it's more efficient that way, because again, I would have these numbers. But the other thing then is evaluating the polynomial, and your text, I think, points this out, is that even though this looks like it would be horrible to evaluate because of, all these multiplications, well, actually it's not so bad, because I could write this as, as Pn of x as a0 plus, and then I could factor out the x minus x0 like that, and then that's times a1 plus, and then I could factor out the x minus x1, and that's times a2 plus, and you see you just keep going this way, x minus x2 dot dot dot. So these things are nested, but you see, well, I'm trying to get this to add a page. There we go. But you see then, what would happen is if I put in a particular value of x, then I could actually start at the very inside. So, this will have dot dot dot, plus, and we'll have our a sub n in here times xn a sub n times x minus xn minus 1, like that, and then all these close brackets like so, and so we could start evaluating here and then just move out of the parentheses. So here's a multiplication, then I would do an addition and a multiplication and so forth. So the evaluation, if you have to do it, is really not so bad if you kind of do it wisely like that. And that's the same for really any polynomial. You can nest it that way, and your textbook points that out. Okay, so let's look at an example. Okay, let's go with suppose we have 0, 1, 2, 3, and we use, I think I used this example for the Lagrange. We'll have a point here at 5. We'll have a point here at 1. -1 will go there, and then back up at 5. Okay, so what we have is our x0, y0 is equal to 0, 5. Our x1, y1 is equal to 1, 1. X2, y2 is equal to 2, -1, and x3, y3 is equal to 3, 5. Okay, so now we're going to just write down this system of equations. So we get a0 is equal to y0, 5. And then we get a0 plus a1 times, now remember that was x, x1, sorry, I was looking back up there and lost my train of thought. So x1 minus x0, oh, well, I don't want to write, I want to actually just do it. So I've got x1, which was 1, minus x0, which is 0. So I have that, and that equals y1, which is 1. And then we had a0 plus a1, and now we need x2, so that's 2 minus x0, plus a2, 2 minus 0, and 2 minus 1 because of x1, and that equals -1. But I need more room, so we'll go 5, 1, -1. Do a little erasing. Okay, and then finally a0 plus a1, and it was x3, so 3 minus 0, plus a2, 3 minus 0, 3 minus 1, plus a3, 3 minus 0, 3 minus 1, 3 minus 2 equals 5. Whew, just barely. And okay, so now simplifying the arithmetic, we get a0 equals 5. We get a0 plus a1 is equal to 1. A0 plus 2a1 plus 2a2 is equal to -1. And then finally a0 plus 3a1 plus 3 times 2 is 6, so 6a2. And here we have 3 times 2 times 1, so that's also 6, plus 6a3 is equal to 5. Okay, so now I can start solving this. I get that a0 is equal to 5. Then a1 is equal to 1 minus a0, which is 1 minus 5, or -4. Then a2 is, well, yeah, a2, I'll divide by 2, I guess, when I do this, is -1 minus a0 minus 2a1, all divided by 2. And so that is -1 minus 5 minus a -8, all divided by 2. So what the heck is that? That's -6 plus 8 is 2. I guess I get 1. And then A3 is equal to A0, well, 5 minus A0 minus 3A1 minus 6A2, all divided by 6. And so that's 5 minus 5 minus, what do we got? A1 is -4, so that's minus 3 times -4. And A2 minus 6 times 1, all divided by 6. So that is equal to, well, 5 minus 5 is 0. Positive 12 minus 6 is 6. Oh, 6 over 6, I guess I get 1 again. Okay, so there are my coefficients, the 5, the -4, the 1, and the 1. And so that tells me that my P polynomial degree 3 of x is the A0, so there's 5, plus the A1, but it's -4, so I'll write -4 times x minus x0, so x0 was 0. Then plus 1, so I'll go ahead and write the 1, x minus x0, which is 0, and then x minus 1, because that was x1, and then finally plus the 1 times, and I'll just write it as x to save a little room, x minus 1, x minus 2. Oh. Well, that was kind of ugly. So this is equal to 5 minus 4x plus x times x minus 1 plus x times x minus 1 times x minus 2. Okay, so that's what we get. And now, you know, again, that's kind of a pain if I want to know, if I want to put in a half, you know, x equals a half or something. You know, as it is, it looks like sort of a pain to evaluate. But again, what we can do is evaluate it as this is 5 minus 4, minus x. Factor out the x. So you see I'll factor out x in each of these, so I'll get x. And actually, to play it safe, I'm going to do a plus, and then, because I'm sure I would get messed up messing with the minus. So plus x, and then I've got the minus 4, and then I have the x plus 1 term, so, and all this stuff. So I've got that left. Well, I'm going to take this and factor out the x minus 1. So this is plus x minus 1 times, let's use a square bracket here and square bracket there. I factored out the x already and the x minus 1, so I just have a 1 left, plus then the x minus 2. And there we go. And so if I wanted to know, say, P3 of, say, a half, you know, I would have 5 plus a half times -4 plus, well, a -1/2 times a 1 plus a -3/2 like that, and end of another page. And so this is equal to 5 plus a half, negative 4 plus negative 1/2 times, and I evaluate that, and I get negative 1/2. So that's equal to 5 plus a half times negative 4 plus a fourth. And so that's equal to 5 plus a half times, well, that's negative 16/4, so minus 15/4. And so that's 5 plus minus 15/8. And 5 is 40/8, so we get 25/8. A little more than 3 1/8, or what, 3.125. Okay, and that's what we get for that evaluation. And so, you know, that is an example of using this thing. Now, the other thing I can do is multiply this all out back here when I had this. So I'll kind of go back and forth. Hopefully you won't get seasick. So the other way to look at this is P3 of x is equal to, okay, 5 plus x squared minus x. So I did that, x squared minus x. Now that's x squared minus 3x plus 2. So I said x squared, but it's times x, so x cubed, plus minus 3x, so minus 3x squared then, plus 2, so plus 2x, and we get that. So altogether, this is 5 plus x minus 2x squared plus x cubed. And if you, oh wait, let's see, what do I have here? Minus 3x squared, yeah, 2x, minus 2x squared, yeah. And let's see, my x term though, let me look back here, did I do something funky? X squared, I get x squared, and then minus 3x, and then plus 2x. Yeah. Well, I'm going to pause it for a second, since I'm looking at this and I'm thinking, that's actually not quite what I expected. So let me pause. Okay, so we were good to here. And actually, in a way, you could actually say we're good to here. The problem is, and I'm going to erase this and go back and show you what I did. The problem was that I went back here and I said, okay, let's take this thing and multiply it out. And I said 5. But then I didn't do the minus 4x. So we've got minus 4x. Then we had the x squared minus x term. Okay, we had that term. And then we had the plus x cubed minus 3x squared plus 2x term. Okay, so we had all those. Then, so that's 5. Now I've got minus 4x minus 5x plus 2x, so I get minus 3x. I get a minus 3x squared plus an x squared, so that's minus 2x squared, and then plus x cubed. And that, yay! That is what we got with the Lagrange interpolation, I believe. I think we did this with Lagrange, but at any rate, yes, that is the correct form in, or the correct answer in standard form. And so, yes, this is all good. So that is the Newton, coming way back here, so quite a bit of stuff, the Newton form of the interpolating polynomial. Okay, so advantages, an advantage on this one is that over the standard form is that this set of equations is quicker to evaluate, okay, because of the lower triangular form there. So that's an advantage over the standard form. However, a disadvantage is it gives you this very nasty form here. That's it's not so bad if you evaluate it the right way, but you can't really see what's going on, right? If I look at that form, I don't know, I really can't see very well what's going on with the polynomial. And so, yeah, I can evaluate it, but that's a downfall, I think. And then a disadvantage from the Lagrange is that it does take calculation. And so there we go.